The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, today we start a new section of data structures. This is going to be 2 lectures long, so this week, succinct data structures, where the goal is to get really small space. And first thing to do is to define what small means. Most succinct data structures are also static, although there are a few that are dynamic. We'll be focusing here on static data structures. And so, in general, the name of the game is taking a data structure that you're familiar with. We're going to talk about essentially 2 today. One is binary tries, which has a killer application of doing binary suffix trees in particular. So it could be a compressed try, whatever. But we'll assume here the alphabet is binary. A lot of this has been generalized to larger alphabets. I'll tell you a little bit about that. But to keep it simple in lecture, I'm going to stick to binary alphabet. And another data structure we're going to look at is a bit vector, so n bits in a row. And you want to do interesting operations like find the ith 1 bit in constant time. These are things that are easy to do in linear space, where linear space means order n words. Like if you want to implement a try, you have a pointer at every node, 2 pointers at every node. That's easy. Bit vectors, you could store an array of where all the ones are. And so it's easy to do linear space, but linear space is not optimal. And there are 3 senses of small space that we'll be going for. One is, the best version is implicit. An implicit data structure means you use the very optimum number of bits plus a constant. But here we're focusing on bits, not words. And if you translate a linear word data structure, order n words is order n times w bits. And to store something like an n-bit vector, you should really only use order n bits, not order n w bits. Okay? Now, what would be ideal is if you use n bits plus a constant. The plus a constant is essentially because sometimes the optimum number is not an integer, and it's hard to store a non-integer number of bits, so you add a constant. I mean, I wouldn't mind too much if you added order log n bits or something, but typically the goal here is constant. Sometimes you can really get 0, but the next best thing would be a succinct data structure, where the goal is to get opt plus little o of opt bits. So the key here is to get a constant factor of 1 in front. And then the worst thing in this regime is still pretty good. It's order opt bits. So for example, if you're storing an n-bit vector, if you use order n bits, that's still better than order nw bits. Usually compact is a savings of at least a factor of w over what you'd normally call a linear space data structure. So this is the big savings, factor w. But there's a constant here. Sometimes you like to get rid of that constant, make it 1. And it's not so bad if you have, say, another, I don't know, square root of n or something, little o of n bits of extra space. But of course, the ideal would be to have no extra space, and that's implicit. Now, it's a little confusing. I usually call this area succinct data structures to mean all 3, but if the middle one is called succinct. That's typically the goal, is to go for succinct, because implicit is very hard, and compact is kind of like a warm-up towards succinct. So this is the usual goal in the middle. And we're going to do this for binary tries and rank and select. So let me tell you a little bit about what's known. One quick example. You've seen implicit data structures. You may have even heard this term in the context of heaps. Binary heaps are an example of a dynamic implicit data structure. They achieve this bound. They have no extra space in the appropriate model. And another one would be a sorted array. Sorted array supports binary search. You can't really update it, so it's a static search structure. It achieves the optimal number of bits. You're just storing the data. And usually implicit data structures just store the data, though sometimes they reorder the data in interesting ways. Like sorting, a sorted array is one way to reorder your data items. So here's a short survey. This is definitely not exhaustive, but it covers a bunch of the main results. So one place where this area really got started, well, there are a few places actually. My academic father, one of my PhD advisors, Ian Monroe, is sort of one of the fathers of this field, and he started looking at succinct data structures at the very early days. And one of the problems he worked on was dynamic search trees. So if you want to do static search trees, you can just store the items in a sorted array, easy log n search, no extra space. What if you want to do inserts and deletes, also in log n time per operation, just like a regular search tree, but you want to do it implicitly? Now this is tricky, and there's an old result that let you get log squared per update and query, which essentially encoded, you can't afford pointers at all here, but the idea was to encode the pointers by permuting enough items. If you take, say, log n items, then the permutations among them is roughly log n bits. And so you could encode bits by just permuting pairs of items. And so you could read a pointer in like log n operations, you end up with log squared. And then Ian Monroe got down to a little bit less than log squared. And then there was a series of improvements over the last several years. And the final result is log n, worst case, insert, delete, and predecessor. And this is by Franceschini and Grossi. And furthermore, it's cache oblivious. You can get log base b of n cache oblivious. So this has been pretty much completely solved. Implicitly, you can do all the good things we know how to do with search trees. Now, this is not trying to solve the predecessor problem using Van Em-DeBose and such tricks. That's, I believe, open. But for a basic log n performance, it's solved. Okay, before this got solved, another important problem is essentially the equivalent of hashing. So you want a succinct dictionary. You want to be able to do, now this is going to be static. So there's no insert and delete. It's just, is this item in the dictionary? So I have a universe of size u. I have n items in the dictionary. So the first question is, what is the optimal number of bits? And this is actually usually very easy to compute. You just take what are the set of possible structures you're trying to represent, which is n items out of a universe of size u. How many different ways are there to have n items in a universe of size u? Come on, it's easy combinatorics. Somebody? Log u of n.
Sorry. That's how many bits you'll need.
Yeah, log u choose n is the number of bits you'll need. The number of different possibilities is u choose n. You take log base 2 of that, that's how many bits you'll need to represent this. Now, this is not necessarily an integer, because it's got a log. That's why we would have plus order 1 if we were doing implicit. It's not known how to do implicit. It's known how to do succinct. So this is going to be plus little o of that thing. And actually, I have the explicit bound. Ooh, eraser. I don't know how exciting this is, but you get to know how little o it is. Log n squared over log n. So this is slightly smaller. So this is roughly something like u log n. It depends. If n is small, this is like u log n. If n is big, this is like n log u, I should say. You can always encode a dictionary using n log u bits. Just for every item, you specify the log u bits. But when n is big, close to u, then you can just use a bit vector and use u bits. So this is little o of n. So it's always smaller than whatever you're encoding over here. It's only slightly smaller than n, log n squared over log n, but it's little o of 1. And that's, I believe, the best known. So this is Brodnik and Monroe, and then improved by POC. And the point is you get constant time membership query. In general, the name of the game is you want to do the queries you're used to doing in something like a dictionary, same amount of time, but with less space. Okay, next one is, maybe I'll go over here. Binary trie, which is what we're going to work on today. There's various results on this, but sort of one of the main ones is by Monroe and Raman. Again, now this is a little harder of a question. How many binary tries on n nodes are there? The answer, I will tell you, is the nth Catalan number, which is a quantity we've seen before. 2n choose n over n plus 1. As we mentioned last time, this is roughly 4 to the n. This is kind of interesting. We saw the Catalan number in a different context, which is we were doing indirection and using lookup tables at the bottom on all rooted trees on n nodes. The number of rooted trees on n nodes was also Catalan number. This is a different concept, binary tries. If you've ever taken a combinatorics class, you see Catalan numbers all over the place. There's a zillion different things. All of them, the number of them is Catalan number. And we will actually use that equivalence between binary tries and rooted trees at the end of today's lecture. So we'll see why they're the same number. Okay, so we take log of that. That's 2n bits. So you need 2n bits to represent a binary trie. And indeed, you can achieve 2n plus little o of n bits. So that's a succinct data structure. And our goal will be to be able to do constant time traversal of the tree. So left child, right child, parent. And for fun, another operation we might want to do is compute the size of the current subtree. Again, think of a suffix tree. You start at the root, and you want to be able to go along the left child every time you have a 0 bit in your query string. You want to go to the right child every time you have a 1 bit. Parent, we don't really need, but why not? And then subtree size would tell us how many matches are there below us. You could count either the number of nodes below you or the number of leaves below you. It's roughly the same for a compact trie. And so this lets you do substring searches. We'll actually talk more about that next lecture, how to actually do a full suffix tree. But this is a component of a binary suffix tree that has the same performance but uses optimal amount of space. And this is a big motivator originally for doing compact or succinct data structures. At University of Waterloo, they were doing this new OED project where Oxford English Dictionary was trying to go online or digital. And this concept of having a CD-ROM that could have an entire dictionary on it was crazy. And CD-ROMs are really slow, so you don't want to just scan the entire CD to do a search. You want to be able to do a search for arbitrary substrings. That's what suffix trees let you do, but you really can't afford much space. And so that was the motivation for developing these data structures back in the day. Things are a lot easier now. Space is cheaper, but still there's always going to be some giant thing that you need to store that if you want to store a data structure, you really can't afford much space. Cool. So that's static. There is a dynamic version. That's a more recent result from just a few years ago. You can do constant time insert and delete of a leaf. And you can do subdivision of an edge. These are operations we saw for dynamic LCA. So same operations as dynamic LCA. You can do these in constant time and still maintain this succinct binary trie representation where you can do all these traversal operations. So we won't cover that. We will cover the static version today. Then that's for binary alphabet. Let me tell you what's known about larger alphabet. This is a problem I worked on a while ago, though our result is no longer the best. So here, it's a little complicated, but the number of tries, number of k-array tries, so k is now the size of the alphabet, is kn plus 1 choose n over kn plus 1. And so it's succinct, meaning we can achieve log of that plus little o of that bits. And the queries we can achieve are constant time, child with label I. And parent and subtree size. So we can do all the things we were able to do before. The analog of left child and right child now is I have a character in my pattern P, and I want to know which child has that label. So it's not the same as finding the ith child of a node. It's the edges are labeled by their letter in the alphabet, and you can achieve that. We had an earlier result that achieved like log or something, and then finally was brought down to constant by Farjan and Monroe. So couple more. Why don't I just mention what they are? It's getting a little tedious. A lot of other things you might want to store. You can store succinct permutations, although there's some open problems here. So you want to store a permutation using log n factorial bits plus little o of n. If you want to achieve succinct, the best known, and the interesting query is you want to be able to do the kth power of your permutation. So see where an item goes after k steps. Best query known for that is log n over log n if you want succinct. If you only want compact, then it's known how to do constant time. So an interesting open question is, can you achieve succinct constant time queries? If you relax either, then it's known how to do it. There's a generalization of this to functions, where one of those results is known, the other one isn't. You can try to do abelian groups. There are finite abelian groups. There aren't too many different ones, and you can represent an entire abelian group on n items using log n bits, which is pretty crazy, order log n bits. And you can represent an item in that group in log n bits and do multiplication, inverse, and equality testing. There's other results on graphs, which I won't get into. Those are a little harder to state. And then another interesting case is integers. So you want to store an integer, and you want to be able to increment and decrement the integer. And you want to do as few bit operations as possible. Worst case, for example, if you have lots of ones in your bit string, you do an increment, you don't want to pay linear cost, linear number of bit updates to do it. And so you can achieve implicit, so just a constant number of extra bits of space. If I have an n-bit integer, then I can do an increment or a decrement in order log n bit reads and constant bit writes. And this is Raman and Monroe from a couple years ago. So this is pretty good. Of course, ideal would be to do a constant number of, bit reads or writes would be optimal, I guess. I personally would be interested in getting a constant number of word reads and writes. But that's an open problem, I believe. So there's only order n bit reads. If they were all consecutive, that would be constant number of word reads, but they're kind of spread out. It'd be nice to get constant number of word operations. So that's a quick survey of what's known. Let's do some actual data structures now. So we're going to be focusing on this succinct binary tries. And we're going to do two versions of it. One of them is level order. And the other will use a balanced parenthesis representation. So let's start with the level order one. This is very easy. So I'm going to just loop over the nodes in my try in level order, so level by level, and write one bit to say whether there's a left child and one bit to say whether there's a right child. Let's do a little example. So here is a binary try, and I'm going to write a bit string for it. So first I'm going to look at the top level. I have the node A, has a left child of B, right child of C, so I write 1, 1. And this corresponds to B, this corresponds to C. Okay, then next level is B. It has no left child, and it has a right child, which is D. I'm just writing down the labels so I don't get lost. Then we have node C, which has a left child and a right child, E and F. Then we have node D, which has no left child, has a right child. Then we have, which is G. Node E has no children. Node F has no children. Node G has no children. Okay, so there is a 2n bit string. This is obviously 2n bits for n nodes. So this is one way to prove there's at most 4 to the n tries. And, well, we'll talk about how useful it is. I want to give you another representation of the same thing, which is if we take these nodes and add on, wherever there's an absent leaf, I'm going to add what we call an external node, as you sometimes see in data structures books. One way to represent a null pointer is say, oh, there's a node there that has no children. This unifies things a little bit because now every node either has 2 children or no children. Another way to think about the same thing. And it turns out, if you look at this bit string and add a 1 in front, so I'll put this one in parentheses, then what this is encoding is just for every node in level order, are you a real node or are you an external node? Are you an internal node or an external node? Right? A here is internal, B is internal, C is internal. This is an external node. Then this is internal, internal, internal. Then external, G, external, 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 external. Right? The zeros correspond to external nodes because those are absent children. So same thing. So I'll write equivalently, one equals an internal node, and 0 equals an external node. Of course, to do this, we need one more bit. And I'm going to take this view primarily because it's a little easier to work with. Doesn't really make much of a difference, just shifts everything over by 1. And I'd like to write down the indices here. So we have 1, 2, 3, 4, 5, 6, 7. Into this array. Because now our challenge is, all right, great, we've represented a binary trie, but we want to be able to do constant time, left child, right child, parent. We're not going to be able to do subtree size. Level order is really not good for subtree size. But left child, right child, and parent we can do in constant time. And the reason we can do it in constant time is because there's a nice lemma, kind of analogous to binary heaps. So the claim is if we look at the ith internal node, so for example, C is the 3rd internal node, so internal node number 3, then we look at positions 2 times 3 and 2 times 3 plus 1, so 6 and 7 in this array, and we get the 2 children, E and F. So that works, 6 and 7 are E and F. Or this one would be the 4th internal node, D is the 4th internal node. And so at positions 8 and 9 should be this external node and G. 8 is an external node, 9 is G. So it works. This lemma, you can prove it pretty easily by induction on I. So the idea is, well, if you look at, let's say, the ith internal node, and the I minus 1st internal node. This one has 2 left children. Don't know whether they're internal or external. Between them, they're on the same level, and we're in level order. So anything in between here is an external node. So they have no children, which means if you look at the children of I, they're going to appear right after the children of I minus 1 because we're level order. So we have these 2 guys. The next nodes at this level are going to be these 2 guys. So this one appeared at 2i minus 2 and 2i minus 1. This one will appear at 2i and 2i plus 1. This is if I and I minus 1 are on the same level, but it also works if they're in different levels. So if I minus 1 is the last node on its level, again, it's going to have 2 children here, which will be the last nodes on this level. And then right after that will come the children of I, again at position 2i and 2i plus 1. Okay, so that's essentially the proof that this works out. There's lots of ways to see why this is true, but I think I'll leave it at that. Okay, so this is good news. It says if we have the ith internal node, we can find the left and the right children, but these are in different namespaces, right? On the one hand, we're counting by internal nodes. On the other hand, we're counting by position in the array, which is counting position by internal and external nodes. This counts both zeros and ones. This only counts ones. So we need a mechanism for translating between those 2 worlds, between translating between indices that only count ones and indices that count zeros and ones. And this is the idea of rank and select. So in general, if I have a string of n bits, I want to be able to compute the rank of a bit, which is the number of ones at or before position I. So I'm given a position like 6, and I want to know how many ones are there up to 6, which would be 5 in the full array here. Or I'm given a query like 8. Number of ones is 6 up to position 8. And then the inverse of rank is select, which gives you the position of the jth 1 bit. So this lets you translate between these two worlds of counting just the ones, which is rank, and or going to the jth 1 bit, that's select. So this lets you compute the left child as just being at position twice the rank. Because the rank tells you this value I, which is which internal node are you. That's your rank. You multiply by 2, and that was the position of the left child. Right child is going to be that plus 1. Parent is going to use select. So if we want the parent of I, this is going to be select of I over 2 with a floor. So that's just the inverse of left and right child. If I divide by 2 and take the floor, I get rid of that plus 1, I get the rank, and then I do select sub 1, and that's the inverse of rank. Okay, so that lets me implement. If I have rank and select in constant time, now I can do left child, right child, parent in constant time. The remaining challenge is how do I do rank and select? And that's what we're going to do next. Any questions about that before we go on? All right. So now we do real data structures. This is going to be some integer data structures, some fun stuff. It's going to use some techniques we know, but in a different setting, because now our goal is to really minimize space. We're going to use indirection and lookup tables in a new kind of way. These are going to be word RAM data structures. I want to do both rank and select in constant time. And the amount of space I have is little of n. I want succinct. I'm going to store the bit vector. So then, in addition to the bit vector, all I'm allowed for rank and select is little o of n space. That's the cool part. So rank is one of the first succinct data structures, and it's by Jacobson, 1989. So first observation is, what can we do with the lookup table? Suppose I wanted to store all the answers, but I can't afford much space. Well, if I had, let's do sort of a worksheet. If I had space x, or if I looked at all bit strings of length x, and then I wanted to store them, that's going to cost, or store a lookup table for each of them. It's going to cost, well, there's 2 to the x different bit strings of that length. Then for each of them, I have to store all possible answers to rank and select queries. So there's order x different queries. You could query every bit. And then for each of them, I have to write down an answer. So this is going to be log x bits, The answer is a value between 0 and x minus 1, so it takes log x bits to write it down. So this is how much space it's going to be to store the answer for all bit strings of length x. So what should I set x to? I'd like this to be a little o of n. So anything that's a little bit less than log n is going to be OK. And in particular, half log n is a good enough choice. If we use half log n bits, this is going to be root n, log n, log n, which is little o of n, quite small as succinct data structures go. We're going to use more space than root n. The point is, if we could get down to bit strings of logarithmic size, we'd be done. But we have a bit string of linear size. So how do we reduce it? Something like indirection. So here's our... The funny thing here is we're going to do indirection twice, kind of recursively, but stopping after 2 levels. The first level of indirection is going to reduce things down to size log squared. So we're going to take our n-bit string, divide into chunks of size log squared n. So there's n over log squared n chunks. They look something like this. Log squared n. And the idea is, right now we're trying to just do rank. Okay, so rank, number of ones at or before a given position. So what I'm going to do is at each of these vertical bars, I'm going to store the cumulative rank so far. Okay. Why log squared? Basically because this is what I can afford. To store that cumulative rank is log n bits. Could be, I mean, this rank is going to get very big. By the end, it'll have most of the 1 bits. So it could be potentially linear. So I'm going to need log n bits to write that down. But how many of these vertical bars are there? Well, only n over log squared n of them. So I have n over log squared n. Things I need to write down. Each of them is log n bits. So there's some cancellation. This cancels with that. We have n over log n bits overall, which is slightly little o of n, and that's the bound we're going to achieve. Okay, of course now we have to solve the problem within a chunk, but we've at least reduced to something aside log squared. Unfortunately, we need something a size half log n before we can use the lookup table. So there's a bit of a gap here. So we're going to use indirection a second time. This time we can go all the way to half log n. So I use red vertical bars to denote the subchunks. Each of these is half log n. Overall size of a chunk here is log squared n. So every one of these chunks gets further divided. Now, how could this help? Why didn't I just subdivide into chunks of size half log n before? I mean, why I couldn't do it is clear. If I did n over log n of them, each of them stores log n bits, I'd have linear number of bits. I can't afford linear number of bits. That would only be compact, not succinct. How does it help me to first reduce to this and then reduce to this? Well, what I want to do at each of these red vertical bars is store the cumulative rank, but not the overall cumulative rank. I only need the cumulative rank within the overall chunk. not relative to the entire array. Okay, why does that help me? Need less bits. These ranks can't get too big because the overall size of a chunk is just log squared. Log of log squared is log log n. So I only need log log n bits to write down those cumulative ranks. And so total size here is going to be n over log n times log log n bits. Because there's n over log n of these red vertical bars. Each one I only need to write log log n bits, and this is slightly little o of n. It's actually a little bit bigger than this, but still little o of n. So we can still afford this. And now we're done because these subchunks are of size half log n, so I can use this lookup table and solve my problem. So, step 4 is just putting everything together. To compute the rank of a query, first thing you do is figure out which chunk you fall into, which you can do by division, integer division. These things are stored in an array, so you just compute what is that cumulative rank. So you take the rank of that chunk, you add on the rank of the subchunk within the chunk, and then you add on the rank of the element in the subchunk. So rank of the chunk is stored in the array known as 2. The rank of the subchunk within the chunk is stored in the array known as 3. And then to compute the rank of the element in the subchunk, you use the lookup table, which is essentially telling you for every possible subchunk what the answers are. So 3 times a constant is a constant. And we get rank, constant time, and n log log n over log n space. If you're concerned that n times log log n over log n is not very sublinear, you can do a little bit better using fancier tricks. Namely, you can achieve n over log to the k n space.